So, hello friends. So today we are going to discuss 3 questions, and these 3 questions are from statics. One second. Okay. So today we are going to discuss 3 questions, and these 3 questions are from the statics. So the first question: 2 identically uniform sticks or rods, each of mass m, length l, are joined by a frictionless hinge at their top ends. The rod stands on a smooth frictionless horizontal table and lie in the same vertical plane. Each rod makes an angle of theta with the vertical. So the 2 rods form a symmetric inverted V about the vertical. A massless inextensible string connects the lower end of the left rod to the right at a point on the right rod such that string is perpendicular to the right rod. The system is in static equilibrium. Assume the rods are uniform, rigid, the hinge is frictionless, the string is massless and taut, and the table provides only the vertical normal reactions. So in this case, I think I forgot to put the question. So in this case, we have to find out the tension as well as the forces because of the hinges. Okay. So these were the 2 questions about it. So let me draw the figure, and the basic figure, suppose this is the table, and on this table we have 2 rods, and these 2 rods are making angle of theta with the vertical, and each rod is having a length of L and mass is given as m. And from one of the ends, suppose we call this as end A, a string is connected to the other rod such that it makes an angle of 90 degree on the other rod. So this is the basic question, and in this question we have to find out the length, sorry, not the length but the tension T, as well as the reaction forces at the hinge. Okay. So let us say that the length of the string is, suppose, D, and therefore we can, and the string where it is connected to opposite end, it is B, and let us call this distance as our S. So we can easily write D and S in terms of L because it is basically a right angle triangle. Okay. And if we extend it in the downward, so this will be also our 90 degree. Therefore, we can say that our S will be equal to L cos of 2 theta, and our D can be also written as our L sine of 2 theta. Okay, these are the two things which we can easily find out. Okay. And first of all, we are going to find out the tension as well as a torque moment balance. Okay. So we are going to consider the left rod, and let me write this as AB, and this point is our P, and let us call this as our Q. Okay, so we are going to consider a left rod. It means we are going to discuss with respect to our rod AP. So you can say, and the hinge we are going to consider is our A. Sorry, not A, my mistake. That we are going to consider as P, because hinge is P and it is connected at P. Therefore, we say taking moments about the hinge P for the left rod. Left rod is nothing but our AP. And for left rod, we can just draw it. So this is our point A and point B, and we are going to have our mg that will be acting in the downward direction, and it will be at a length of L by 2, and with respect to the vertical, this angle is our theta. Therefore, the lever arm length will be equal to L by 2 sine of theta. Sine by theta. Therefore, we can say or write that the weight torque, you can say that torque due to weight, and let us call this as tau W. So we can write the equation about tau W will be equal to our mg and L by 2 sine of theta. And next, we are going to consider the string, and so for the string, let me draw the figure again. So we have our AP, and this is the other part, that is our Q, and the string is drawn from our A, making angle of 90 degree to our B. So this is our string, and AP with respect to the vertical is making an angle of theta. So first of all, we are going to find out what will be the angle made by the string to the horizontal. Okay, so horizontal, we can just join this, and in this case we are just going to consider the, because we know this angle is our theta, so we have this is 90, so obviously this will be over 90 minus theta, and in the other triangle this is 90. Okay, so this angle will be our theta. Okay, so we are going to consider two triangles, and based on this we found out that the string AB makes an angle of theta with the horizontal. Okay, so that was very much required. Now we can just easily find out our tension T, and suppose the string is our tension T, and we can divide this into two components. One will be coming as T cos of theta, and other one will be coming as T sine of theta. And along with this there will be also a normal at A. Okay, let us call this as normal at A. And as usual, the length we already know, AP is given as our L. This is known to us. So let's find out. There are two components, vertical component T sine of theta and the horizontal component T cos of theta. And so next we can say tension T components, and first component is our T cos of theta, and because of this we can also find out the distance of our T cos of theta, and this distance, that will be our lever arm, will be our L cos of theta, and the other side will be our T sine of theta, sorry, L sine of theta. So this T cos of theta is going to produce a moment, and that moment will be equal to our T cos of theta multiplied by L cos of theta. T cos of theta times L cos of theta. Okay. So this can be written as our TL cos square theta. Okay. This was because of our T cos of theta component, and the second component is our T sine of theta, and the moment because of this T sine of theta will be our T sine of theta, and T sine of theta in the lever arm distance is our L sine of theta. So this will be coming as our TL sine square theta. Okay. And so these contribution, because of these two, our T cos of theta, that is the horizontal one, and T sine of theta, that's a vertical one, we can find out the net torque. Therefore we can say the net torque, and let us call this as torque because of the tension T, which will be equal to our LT, we can take as common, so this comes as TL, and they will be in the opposite direction. Therefore we can write it as our cos squared theta minus sin squared theta. And for the trigonometric identity, we can say tau t can be written as our TL cos of 2 theta. Okay. So this is the torque because of the tension T. And there is also normal NA. Okay. And its distance is similar to our L sine of theta. Okay. Therefore we can say that normal, or let us keep it n for the sake of simplicity, okay, much more easier. So we can say that the normal n will be giving us a torque. Let us call this as our tau n, and tau n will be the force and multiply by our lever arm, that is n sine of theta. Now we have our, you can say, 3 torque equations. First torque is because of our mass mg, that is our weight. Then is our because of our tension T, and finally because of our this normal. And it is given that your system is in static equilibrium. Therefore we can say for static equilibrium we can, okay, and please remember everything is being calculated is with respect to the hinge P. Okay, hinge P means with respect to this point. So for static equilibrium we can write the equation will be our tau of T minus, and we have our tau of n, and plus tau of our weight is equal to 0. So we simply substitute these values. So tau of T is our TL cos of theta, tau of n is our NL sine of theta, plus tau of weight is mgl by 2, and we have this as sine of theta is equal to 0. And we can simply go make away with this L, and we are going to keep this equation as it is and solve it later on. So let me rewrite it. So this comes as T cos of theta minus n sine of theta plus mg by 2 sine of theta is equal to 0. And we can just redraw the horizontal part. Okay, so we have the rods which are something like this. Okay, and everything is symmetric. Therefore normal at A, which is given as our n, and our normal at our, I think it was Q, that will be also our n, and first rod is going to have downward in mg, other rod is also going to have our downward in mg. Okay, so everything is in equilibrium. Therefore we can write that upward forces are n plus n, which will be equal to our mg plus mg. So which gives us that our n is equal to our mg. And we are going to put n is equal to mg in this equation. Therefore we get this as T 1 second. This is 2 theta, not theta. 2 theta, 2 theta, and it is n of sine theta. Rest is okay, I think. So we can write this as our t cos of 2 theta minus mg sine of theta plus mg by 2 sine of theta is equal to 0. And we can solve this, combine this part and solve it for our t. Therefore we can say our t is equal to, denominator we are going to get this as our cos 2 theta, and this will be coming as minus and this will be plus. So we get this as our mg sine of theta, and this comes as 2. Okay. So this is our tension in the string. Okay. And next we are interested in finding out the hinge force, which was a part B. I forgot to mention there in the question itself. So we have our part B. So in part A, we were supposed to find out this tension T in the string. Okay. And part B, we are going to find out the hinge force. And therefore okay, so let us still we are concentrating on our left rod, and this is going to have our tension was having two components. 1 second. T cos of theta and T sine of theta. Yes. So we were having a tension T cos of theta and our T sine of theta. Okay. And along with this, there was a normal, and also we were having mg in the downward direction. So these were the forces which were already discussed. And this is our string. It was making an angle of theta, so the tension T with the horizontal. And so this is our A and this is point P. Okay, so we can say for AP at point P, we can write that for horizontal equilibrium, we can write this will be equal to our h of x plus t cos of theta is equal to 0. Okay. And from here, okay, I forgot to mention this h of x. Okay, 1 second. So this is our P, and the hinge force will be in this direction, that is our h. So we can say this is our h of x and this will be our h of y, because h is acting, this is our h hinge force at P. Therefore we can write that our h of x is equal to minus t cos of theta. And for our vertical equilibrium, vertical equilibrium, we can write that h of y plus n plus t sine of theta minus our mg is equal to 0. But we already know that our n is equal to mg. Okay. Therefore, because this is our mg, so these two terms cancel out. Therefore, we get that h of y is equal to our minus t sine of theta. And so these are our hinge forces. Okay. So obviously the force they are going to act with respect to each other will be opposite to this. Okay. So therefore we can say that by Newton's law, the force the left stick exerts on the right stick is opposite. Which basically means that the force x component will be over t cos of theta and its y component will be equal to t sine of theta. Okay. Here, okay, this you can further modify because we already know our t tension we found out is our mg sine of theta cos of 2 theta. Therefore, we can substitute it and we get our f of x is equal to, we get this as our cos of 2 theta 2 and we have here our mg sine of theta cos of theta. Similarly, f of y is equal to our cos 2 theta 2 and this comes as our mg sine square theta. Okay. So these are the forces, tension as well as our forces that were acting. Okay. We come to the next question. And next question states that two slender uniform rods are connected by frictionless hinges. One end of the top rod is hinged to the vertical wall and the other end of the top rod is hinged to the left of the bottom rod. The bottom rod is horizontal and has length L. Two rods meet at the interior hinge and make an angle of theta with each other. Both rods have same mass per unit length lambda. The system lies in a vertical plane and is in static equilibrium. The hinges are frictionless and the rods are rigid. Find the horizontal and vertical component of the force that the wall will exert at the top hinge. Same question, but it in a different way. Okay. And we have part B also. Show that the magnitude of this hinge force diverges or tends to infinity in the limits theta 0 and theta to pi by 2. Okay. So if we are able to drive the equations, we will able to easily prove with respect to these two limits. And we can just draw the basic figure. So we are given a wall and to this wall there is a rod of length L which is perpendicular. So this is our rod of length L and it is perpendicular, and we have other rod which is connected to wall and it is making angle of theta with the this rod. So this angle is given as our theta. And let us call this as A, this point B, and this point C. So we have to calculate everything with respect to point A. And okay, so we can so it is given that everything is in equilibrium. So we are going to discuss it into two parts. First will be with respect to rod BC and point C, and other one will be rod AC with respect to point A, and then we are going to solve this. So we say equilibrium of the horizontal rod and connected to rod C and connected to rod C. So we are interested in this our point B, and this is point C. Length is given to us as L, and this is our coming from A towards C. Okay. And we are going to have this angle is given as our theta. So there will be we are going to mg of our of BC in the downward direction. Let us call this as weight B, WB. And so there will be a reaction of the wall on this B. Let us call this as our R of X. Therefore, we can write it as reaction at wall B, or we can put it forces on bottom rod. And so first is our reaction at B, which we called as our R of X. Okay. And the second one will be the force from the top of the rod from A to C. Okay. So you can say force at C from A. So obviously it is going to have two components. We can call them as our f of x and f of y, because it will be acting at an angle, something like this. So we can say this is our f of x, and we are going to get this as our f of y. And the weight will be at a distance of our L by 2. So this is L by 2 as well as this is our L by 2. So for horizontal equilibrium, so you can say for horizontal equilibrium, can write that our f of x plus r of x is equal to 0. Therefore, we can say that our f of x is equal to minus of r of x. And for vertical, we can write that our f of y plus f of, okay, say that both are in negative direction, so we can write this as minus f of y minus w of b is equal to 0. And this gives us that f of y is equal to minus w of b. W of b is nothing but our weight. And furthermore, now we come to our rod which is at an angle. So we can say equilibrium of a rod AC and for that we are almost going to draw the same figure. So this is our A, we have our C, and this is our B, making angle of theta. But we are interested in our now AC, not our BC. BC we have already solved. And so for this, let us suppose C is center of mass, so it will be the downward direction. Okay. And let us call this as our W of C. And there will be a this direction, so we can divide into two components. This we can call this as our h of x, and this we can call as our h of y. Okay, and yeah, I think for the time being this is sufficient. And therefore we can say that forces on the rod AC, forces on the rod AC. First one is our, because it is hinged at A, so we can say wall hinge at A. And we are interested in these two components, not the individual one, so we can write this as h of x as well as our h of y. And the other force will be the bottom rod that a BC is going to exert on point A. Okay. So you can say that bottom rod is our BC exerts on hinge A along AC. So obviously its direction will be just opposite to these two, f of x and f of y. So we can just take their opposites. We can write this as minus f of y, and in this direction we get minus of f of x. Or which we can write this as minus f of x and minus f of y. And we have a weight WC acting in downward direction. and we have weight, that is our WC. So we can use the equilibrium for static. Therefore we can say that for static equilibrium, for our horizontal, we have our h of x and we have our f of x. So we get this our h of x minus f of x is equal to 0. We get here h of x is equal to our f of x. And then we come to a vertical, and vertical we are having h of y, f of y and wc. So we can write this over h of y minus f of y minus w of t is equal to 0. So from here we can say our h of y is equal to f of y plus, sorry, it is w of c, not t, w of c. And now we can also find out the respective moments. So we can say that moment of wall force H about C, and this will be having, okay, before that we have to solve for our position vectors, and then we can find out its, okay, let me find out the position vector of the respective, and then we can use the scalar moment concept. Okay, so we can say that our the moment about C, it can be written as our tau is equal to our x multiplied by the y component minus y multiplied by our x component. Okay, because this is, one second, yeah, and this, let me write it other way. This doesn't. So you can say, because we are calculating with respect to C, moment about C, and we are going to take anti-clockwise as positive. Anti-clockwise will be taken as positive. First of all, let's define the position vector of our A. So we can say our position vector of A relative to C, and if we draw, so this is our A point, this is our B, and this point is C, and this angle is given to us as theta, and length BC is our L. Therefore, the position vector of A relative to the C, it can be written as our negative of our L, and then the Y will be coming as our L tangent of theta. So these are the X and Y position vector of our coordinate of our A. Okay. And now we can easily solve it. So we can say that moment of the wall force, which we denoted as our H, about C. But this H was having two components, H of X and H of Y. Okay. So therefore we can write, because we were having our H, and this will be coming as minus L times our H of X, because this was our H of X and this was our H of Y. And minus, and we have our L tangent of theta, sorry, this is H of Y, okay, because H of Y is the lever arm distance is over L, and the minus L of tan theta, and this is our H of X, and there will be a weight that will be plus L by 2, and we have this as W of C is equal to 0, okay, because this is our W of C, and that will be equal to 0. And we can just cancel out our L here, so this L and L goes away. Therefore we are left with only minus H of Y minus tangent of theta H of X plus 1 by 2 W of C is equal to 0. And from here we can write that our H of Y is equal to minus tangent of theta H of X plus 1 by 2 W of C. And we already know that our H of Y is F of Y plus W of C. So we can substitute it here. So in place of H of Y, we can put over F of Y plus W of C is equal to minus tangent of theta plus 1 by 2 W of C. And we can combine this W of C, therefore we get this as our, here it is H of X. So we can write this our H of X tangent of theta is equal to minus F of Y and minus 1 by 2 W of C. And we also know that our H of X is equal to F of X. Therefore we can say that our F of X is equal to, this will be our minus f of y minus 1 by 2 w of c and tangent of theta. And our this f of y was is equal to our minus of b, wb. Okay, so we can put it here. So we get this as our tangent of theta, and it will be coming as our f of y was minus w of b. So minus minus plus, so this will be w of b minus 1 by 2 w of c, and we can just solve it further if required. Otherwise we got that f of x is equal to, we can take 2 as LCM, so this comes at 2 tangent of theta, so we get this as twice w of v w of c. So this is our f of x. Okay. And we already know that our h of y so our f of x was nothing but our h of x. So this is nothing but our h of x also. And we know that our h of y is our f of y plus w of c. F of y plus w of c. And f of y is our minus w of b, so we can write this as our minus w of b plus w of c. Okay. And if required we can put w of c also, or otherwise we can keep it as it is. And or we can write it in the form of our, I think we can keep it as it is. There is no need to put the weight equation in terms of the lambda. Okay. So this was the second question, and we come to the third question. Third question, it states that a uniform stick of length L rests in a static equilibrium touching a fixed circular ray object of radius r as a tangent. Let the stick make an angle of theta with the horizontal. So here we have to find out two things. The coefficient of friction between the stick and the circle must satisfy this equation, and the coefficient of friction between the stick and the ground must satisfy this equation. Okay, so these are the two things which we are going to prove. And in this case we are given that the length is our L. Okay. So we can just draw the basic figure for it. So suppose this is our circular object and it is placed on the ground, something like this, and then a stick is acting as a tangent, somewhere something like this, of angle theta. Let us call this as A, and this point is B, center as O, and this is our radius is our R. Okay, so this is the basic figure. And So there will be a normal at A, let us call this as our NA, and there will be a normal at B, and let us call this as our NB, and there will be a friction, let us call this as F of A, and this is our F of B, and the total length is given as our L. So there will be for mg by downward direction at a distance of over L by 2. So these are the basic things that are given to us. And first of all, let us find out the point B. Okay. And in this case, it is not actually mentioned what will be how this rod is placed. It is simple said that it is placed acting as a tangent. So this length can be on the higher side also, and it can be on the just touching the chord. Okay. So for the sake of simplicity, because from the solution we can clearly understand that the coefficient of friction in the both cases is independent of the length. Okay. It is only dependent upon the sine and cosine of the angle theta. Therefore, we are going to assume that the rod and the point of contact B is having a length that is our S of B. Okay, and based on this we are going to solve it, and later on we can deal with it. Okay. Therefore, we say this is point A, this is point B, and angle theta. So this we are going to assume that this length is our S of B, and this point B is the touching the contact point. Therefore, we can write that, let us call this as our C. Therefore, this will be our FB cos of theta, and this can be written as FB sine of theta. So what we did, we considered that we say that let the distance along the rod from A to the tangency B is our SB. Therefore, we can write the coordinate of our B will be our SB cos of theta and our SB sine of theta. Okay. And now we come to the normal part with the center of the circle is given as O. Therefore, we can say normal to the stick at B points from B towards the circle center O in direction, and the direction we can write this as our minus sine of theta and cos of theta. Therefore, we can write the center O will be equal to our b plus r minus sine of theta and cos of theta. And b we already know, so we simply substitute it. We get this as our O will be equal to, then we have our b is our x coordinate sb cos of theta, and here it is minus r sine of theta. Therefore we can write this as our sb cos of theta minus r sine of theta, and it is sb sine of theta sb sine of theta plus r cos of theta. So these are the coordinate of our O. So we have our, this is our r, so this is our x and this is our y. But if you look closely, the y coordinate is nothing but our equal to our radius r. Therefore we can say that because the circle sits on the ground, its center height is nothing but its y coordinate, which is our radius of the circle. Therefore we can write that our sb sine of theta plus r cos of theta is equal to our r. From here we can write that our sb will be equal to r1 minus cos of theta divided by sine of theta. Okay, this we are going to use later on. And now we come to our the forces as well as the moments balance, because it is given it is in static equilibrium. So we can say the moment balance about A. And we are going to calculate point A. So this is our point A and this is our point B. So this is normal here, and there will be mg in the downward direction, and the total length is given as our, because the length is, let us put like this, so this length is our L, and point B is at a distance of SB from A, which we already defined. So mg will be at a distance of our L by 2, and this is a normal M. Or for point B, NB. Therefore we can say moment balance about A, and we can write this as our, first is our weight mg, and we can write it's our moment will be equal to over mg, and we have our this distance, angle is theta, so the lever arm distance will be over L by 2 cos of theta, cos of theta. So this comes as L by 2 cos of theta, and then we are having normal at B, normal at B, which is our NB, and the distance is our S of B. And friction will be acting at the both point will be along the rod, so we are just going to ignore it. And for equilibrium, we can write that our mgl by 2 cos of theta will be equal to our nb multiplied by s of b. Therefore, from here we can write that our normal at B will be equal to, this comes as twice S of B mgl cos of theta. So this is our normal. Okay. And S of B we already know, so let me substitute it. So we can write this as our mgl upon 2, and S of B is our r1 minus cos of theta. So this comes as r1 minus cos of theta, and it comes as our sine of theta and cos of theta. So this is our normal at B. And now we can use the force balance equations and solve it further. So we can say our force balance, okay. And so this is our horizontal, and we have a rod, and this is our A and point B, angle of theta. So first we is our normal NA and friction FA, and then we are going to have a normal NB, and we can divide this normal NB into two components. So this will be angle theta, so this will be also theta, and we get this as 90 minus theta, and this will be a theta. So we get this as a NB cos of theta, and we have our NB sine of theta. And then our friction is left, so we can say this is our friction at B, F of B, and we can divide it into two components. So this will be coming as our theta, so we have our FB cos of theta, and here we are going to have FB sine of theta. And what else? mg. So these are the various forces in their respective component forms, horizontal as well as our vertical. Therefore, for horizontal equilibrium, we can write that our f of A plus fb cos of theta, we can just take this value of x-axis and this value of y, and we have our f of B cos of theta minus n of B sine theta is equal to 0. And vertical equilibrium, we get our NA plus, so we get this as our FB sine of theta, and plus NB cos of theta is equal to 0. So these are the, and what else, minus mg is equal to 0. So these are the two equations for our this. Now we are interested in finding out the, you can say, the value of the friction in the both cases. Okay. So first of all, we are going to find out the minimum circle friction. Let us call this as mu of c. Minimum circle friction, and that is our mu of c. Okay. And this is because it is in static equilibrium, and therefore we can say, or we can simply first of all write the equation for our friction at B will be equal to the circle friction as well as our normal of B. Okay. And we can put this value of friction in both the equations. Okay, so that is equation number 1 as well as equation number 2, and solve them. The rest is now our only solution part is left. More or less everything is done. So we can say from equation 1 and 2. So we can say that our f of a, one second, what the hell, okay, I've written this, this is f of a, that's correct. So we have our friction f of a will be equal to, we have our NB sine of theta minus FB cos of theta, and FB is mu Cn of B. So we can take as n of B as common. So this comes as our sine of theta minus mu of C, and this is our cos of theta. And similarly, we can write that our n of A will be equal to our mg minus n of B cos of theta plus mu of C sine of theta. But physically, for static equilibrium, we should be knowing that our n of A should be greater than equal to 0. So we can say that for static equilibrium, our n of A should be greater than equal to 0. Because if the normal is less than 0, the stick, because it is connected at point A, so the stick is connected at point A. If the normal at A is less than 0, the stick will lift and there will be no static equilibrium. Okay. So we consider the limiting case. Okay. So we can say for NA equal to 0, that is our limiting case, and we can put in this equation, we get this as 0 is equal to our mg minus n of b cos of theta plus mu of c sine of theta, and we get from here, we can write our mu of c will be equal to sine of theta, and this comes as our mg by nb minus cos of theta. And we already know that our n of b, let me write it here, n of b we already know is our mgl cos of theta, and this is twice time s of b. Therefore, and we need this ratio, so you can just easily write it from here. We can say that our mg upon n of b will be equal to twice of s of b, and we are left with L cos of theta. So we get our mu of c is equal to, this is our twice s of b, L cos of theta minus cos of theta and sine of theta. Further simplification gives us L cos theta sine theta twice s of b minus L cos square theta, that is our mu of c. And s of b is our r1 minus cos of theta divided by sine of theta. So if we substitute it here, we get this, our mu of c is equal to sine of theta divided by 1 plus cos of theta. And this we considered using the limiting case, but we already know that our mu of c should be greater than or equal to our sine of theta 1 plus cos of theta. So this is our first part. And for the second part, part B, similarly we are going to discuss that we require a minimum ground friction. And that coefficient is called as mu of g. Okay. And once again, the limiting case, we are going to assume that our f of b is equal to 0. Therefore, we already having two equations, and one second, yeah. So equation number 1 and equation number 2. So you can say from equation 1 and 2, equation 1 and 2, we put fb equal to 0. We are going to get this as our, sorry, this is capital F, not small f. So we get our f of a is equal to our nb sine of theta, and we get our n of a is equal to mg minus nb cos of theta. Okay. And nb we already know is our mgl cos of theta twice sb. Okay. So we already know that our n of b is our mgl cos of theta twice sb. and our mu of G we know is our f of A upon n of A. Therefore, we simply take their ratio. So we get from here mu of G is equal to f of A upon n of A. It comes over NB sine of theta mg NB cos of theta. And S of B, we also know S of B is equal to R1 minus cos of theta divided by sine of theta. So we are going to use our N of B as well as S of B and solve for this. And we are going to get that our mu of G should be greater than or equal to sine of theta cos of theta 1 plus cos of theta and 2 minus cos of theta. So we got the friction between the rod and the ground, that is a mu of G, friction coefficient mu of G, as well as the circle coefficient, that is the tangent and the circle mu of C, is satisfying the given conditions. Okay, that was the question asked for it. Okay. So these were the 3 questions from the statics. Thank you.